near neighbor connections, it's completely randomized. But the connections inside are the same, and the total number of nodes, the same. The number of connections between the brain and the spine, also the same. In every case, we try to preserve the features, but leaving the finer details, like I said, up to chance. And for those of you that are been here, we've been talking about scale freeness. This right here, this reordered ring lattice, it is intended to be I said scale free, I meant small world, I'm sorry. It is intended to be a small world graph, right? You create a ring lattice, you rearrange some of the connections, you create shortcuts, and this graph should be highly small world. Small world structure should be throughout the entire thing. And just for the sake of doing it, we also made a completely random model. This is just completely uniform, random connections, but the same number and the same number of nodes. So that's wonderful. Now, to actually test these things, we wanted to analyze some of the underlying functional advantages that other networks like we just talked about have, and so we wanted to test some certain features. And one thing we wanted to look at was small worldness, like how small world is a graph, which is intriguing. It's been defined typically using characteristic path length and like clustering coefficient, and in fact you can actually come up with a really nice metric if you just take the ratio of those two things. T here is a test graph, so that's the graph you want to measure. This R is a completely random graph with the same size and order. And then you make this, this very crazy looking ratio, and you get a single real number that represents how small world a graph is. It's a little dependent upon the size and order, but it's okay. If you have a non-small world graph, completely random, you get a measure of about 1. Whereas really small world graphs that really exhibit small world structure, you'll get something much higher.
So what's the clustering coefficient of T?
The clustering coefficient of T is just, so the clustering coefficient just all by itself is the measure of how closely neighboring nodes are connected. So there's, like, think of it as a group, like you take a little cluster of neurons, nodes, and you ask the question, for that little cluster, how well connected are they? It maybe also can be thought of as a measure of the number of small triangles in a graph. Something to that effect. It's a little bit more detailed, but that's essentially what it is. For the random graph, it's a little more nebulous because it's a random graph, but it certainly makes sense for your test graph. Good question though. Characteristic path length is the average shortest path in the graph. I don't know. That is unknown as well. But good. So then I was jumping myself earlier. This is scale free now, and we want to talk about that. And it is defined as simply the degree distribution of the graph following a power law. And a power law just looks like this, right? You go down, or on a log-log plot, you have a straight line. Same thing. I'm kind of more of a fan of this size here. It looks very cool. Why are they interesting? They're resistant to random attacks. You know, there's hubs. There's little nodes all over the place. You take a little node that's there, and it's a little more meaningless to remove. And so we want to look at that. And something a little more biologically important, a little more verification, is neuron ablations. We want to take our model, simulate something they actually do in the laboratory, and see if we get similar results. And so one thing that they do is have seen is that with the ablation of certain neurons, there is an increased latency in certain escape responses. So you stimulate the fish on the side, the fish turns away to avoid that, and you see how long it takes for that response to be evoked. And ablating some of these certain neurons causes a latency in that effect. And so we want to remove these neurons in our model. These are the Mothner series. That was the largest neurons in the brain. We want to remove them, and we should expect to see fewer paths, individual paths between the neuromass and the sensory cell and the motor neurons, but we should still see connectivity. That was the most we could go on for right then. But it's important to know that we're only restraining ourselves to functionally relevant paths, which are probably only 3 or 4 connections long. Certainly there's probably some path in there that's, 100 paths to the motor neurons, but that's not going to matter because the signal's not going to be able to travel that far. And this is the image that we're kind of looking at here. It's a nice little strange thing. Here we have the neuromass of the fish. There's 15 of them, and here we have spinal segments, right? And the height of this surface is the number of unique paths between those neuromass and that spinal segment. So this is an interesting shape that I unfortunately don't have time to talk about, but it is not something we plan to see, and it's something we hope to look for in the future. So now small worldness, we took and we calculated this small worldness metric that we came up with, and we did it on all our test graphs, and we get something like this. It's no surprise, right, that the random ring lattice has the highest measure because it was intended to be small world. And it's right about 19, so that's good. And the random right here, it's right at 1. It's 1.003 or something, which is also good because it was supposed to be low. The random compartmental model comes in at just a shade over 1, about 1.3. And here we have our anatomical model at about 4.5. So this is strong evidence that our model actually is small world, which does conform to other neural networks. So we take this as a sign that we're headed in the right direction. For scale free, we wanted to analyze our degree distribution and see if it follows the power law. That's our degree distribution. So you maybe think about for a second, does this follow a power law? Well, no, it does not. No. So we did some AIC on it for model selection, and the power law fit is actually extremely poor. So we can conclude that this is not a scale-free model. Another bone in contention of the debate going back and forth whether neural networks are actually scale-free or not. In the literature, there are examples of both. And the neuron ablation, we did it and we compared the before and after, and we get an image like this. So these are number of unique paths of length 4 between neuromass. So like you can imagine the little fish here and the little fish here. And what we see in this image is that there is a large difference, up to 1,000. But what you don't see in this picture, but it is there, is that there are still connections between them. And I wish I had time to talk about this interesting structure. Again, something we didn't plan, but maybe something that it could be experimentally verifiable, because it appears that that the most damaged circuits are those between middle neuromass and the entire length of the spine. Something that might be verifiable in the lab. So what have we done? We have created a realistic, who knows what that means, you know, anatomically based model of the zebrafish posterior lateral line sensorimotor pathway. We measured the small worldness of this network and several others, and we can conclude that it does have a comparable small worldness to other neural networks in the literature. The degree distribution shows no evidence of scale-free, which again, just another bone to pick in the fight. And this simulation kind of verifies results. We see latency, we see fewer paths, but there is still connectivity. And something we didn't see here is that these results are rather robust. We have done some heavy changing on this model, and these are the results. They just keep popping up. So there's something inherent in the basic structure that makes all this work. Wonderful. So this is not the end of the road. These are all the beginnings of something hopefully better. We want to put dynamics on this. You're probably thinking of it. I was thinking it. We were all worried. Dynamics on this model are missing. That's the one thing that's really not there. And we're certainly going to do it. And one of the first things we wish to do is, as you know, there's excitatory and inhibitory connections in the brain. And if we include those, is it possible we can see an actual escape response with the right stimulus? Also, is it possible to optimize the brain? The connections in the brain are largely assumed. They're hard to figure out. The assumptions we went with are pretty straightforward, pretty basic. But is there a more optimal way of having the configuration in the brain for speed of path being transferred? We hope to do this in the future. That's what we're headed towards. Just in closing, if you want any references, there's a whole bunch. the early manuscript that we've written or comments, please email me. I'd love to talk about it. And thank you for listening. Are there any questions?
We have time for questions.
So you made a comment about the in the scale-free. You said it was robust to some attack.
Yes. So.
Sorry, I didn't know what that was.
Oh, very good. So in a scale-free graph, right? One of the structural features of scale-free graphs are the presence of hubs, right? If we go back maybe here, we can see just this degree distribution that we looked at. Right there. So if we look at this, what this degree distribution is saying is that there's a lot of nodes with very low degree, and there are a few really high. These really high degree nodes operate as hubs or central processing units that allow the traffic to flow through, much like the internet or something with major processing centers. So if you were to randomly attack the network, where would be the most likely place you'd hit? It would be one of these non-essential pieces. So those non-essential pieces you can pluck out and you don't really hurt the system. If you take one of these big bad boys, then you're going to really damage something. That is why it's thought to be important. Yes?
When you were trying to the small world metrics,
Yes.
so why did you choose to use a random model to compare the actual test that you're using?
Right. I think of this before this. Yeah, so we're using this random graph for comparison purposes. It's small world structure is defined by this surprising presence of very short connections between nodes. So the average distance between nodes is really short. Random graphs do not have this property. They're completely random. It's uniform. It makes for the best starting place to compare it against. That's really all that we do it for. Just a good starting place. There's no assumed structure. What's his name? It's the classical definition of a random graph, right? That is a starting place. So that's what we did it for. Got it?
Yes. So you were looking at some sort of a single statistic which describes your network. But your network was actually quite inhomogeneous in many ways.
It is, absolutely.
Some parts of it could be small world, other parts of it could be scale-free, and
absolutely. And that is another thing that we didn't talk about. But actually, in looking at scale-freeness, we shouldn't have even assumed it was going to be scale-free because the components are so varyingly different. If we look at our degree distribution, we can see these features actually. You see, just because this is a large region, it doesn't correspond to the brain, of course, but that's what these are. These are a lot of connections in the brain. The brain is highly connected, and so certainly there might be some scale-free features in the individual components, but we wanted to see, does the entire pathway as a whole scale-free? And no, and we shouldn't have thought so, and it's certainly not the case. But thank you.
So in our model, we keep track of all the names of all these neurons, all these nodes, and one thing we were working on is having code that will pull out certain nodes of certain degrees, so we can look at that. Because you'd be tempted to say, oh, the beginning's the lateral line, and the middle's the brain area, but we can't say that. So
you're keeping track of which is
conditional distributions in some sense.
Absolutely, absolutely. Great. Thank you very much, everyone.
Great.